In this section, we're going to look at another test to see whether certain series converge or diverge. And it's called the integral test. And then there's the p-series. There's just conditions for p-series. So, and it comes from the integral test. So that's why we're going to do these both together. And it's not terribly difficult. I'm just going to write down the integral test. There are three conditions that need to be met first, and then you are allowed to use the integral test. So I'll write those three conditions first, and then we'll continue from there. So we've looked at geometric series, and you can use the formula for the sum of an infinite geometric series if it follows certain criteria. Also, you can use the techniques for telescoping series if, in fact, the series is a telescoping series. But that's pretty much all we've learned so far, I think. And now I can't remember. But like, how do you know when you're allowed to use the integral test for a certain series? So the first thing you do is you change your series into a comparable function. It's pretty much, instead of a sub n, you just change it into f of x. But we'll see that in an example. So that's the first thing you do, and then there are three things that you need to check. If all three of these things are satisfied, then you are allowed to use the integral test. The first condition is if your function is positive for x greater than or equal to 1. It's pretty much just, is it positive for wherever we're looking at the series? And if your function is continuous for x greater than or equal to 1. This is actually not super strict. We can actually change it to greater than 1, or later on down the line, it's greater than any other number. But we're just going to say this for now, and hopefully later on you'll begin to understand how you can manipulate that. But, so these two things have to be satisfied. And if your function is decreasing for x greater than or equal to 1. So if all three of these things are satisfied, then you are allowed to use the integral test. So those are the conditions that have to be satisfied. Now, these two things you can verify just by inspection most of the time. So it's not really required that you show that these things are true, that these two conditions are true. If your function is positive for x greater than or equal to 1, you can just look and see, and it'll be fairly obvious. And then also, if your function is continuous, we can just use the fact that polynomials are continuous, the natural log's continuous, e to the x is continuous for x greater than or equal to 1. And if you have a rational function, just look and see if you can get 0 in the denominator while only having x values that are greater than or equal to 1. So that also will be easy to do by inspection. The last one is where you'll have to show something. This is fairly common on most tests. If your function is decreasing for x greater than or equal to 1, and we can figure that out, we can show this by taking the derivative and seeing if it's, negative for x values that are greater than 1. So those are the conditions that you'll need to have satisfied before you use the integral test. So if all three of those conditions are satisfied, then we can say some things. So the actual integral test is saying, suppose you have some series where it's n equals 1 to infinity of some sequence. You're adding up some sequence. Okay, so you have this series, and then you make, this is what I was talking about, you make your function by replacing the n's with the x's. You make your function by taking your formula there and just changing it to x's. That's this part. And suppose all three of these are satisfied, which you'll have to verify at least the last one. And then if the improper integral of that function from 1 to infinity, or if this says like 3, then this would be 3. They have to have the same limits. So if the integral converges, then so does the series. If the integral diverges, then so does the series. So there's no question about this one. It's just yes or no. Like there's nothing that we don't understand about it. It's not like this test can be inconclusive at all. It's always going to be either converging or diverging based on the corresponding improper integral. And that's pretty much it. That's the whole entire integral test. We'll use it for at least one example. It's fairly simple. All we're going to be doing really is just evaluating improper integrals. So that's the test. All three of these have to be satisfied. If the improper integral converges, then so does the series, or if it diverges, then so does the series. Something to mention, though, that the integral test doesn't tell you what it converges to. So we may get like some number for the improper integral that it converges to. That is not the same as what the series converges to. So I'll write that. So it tells us whether it's convergent or divergent, not the actual value of the series. So it's not the same as geometric series where we can actually find out a value. All right, that's it. On to examples.